Today's focus will be about particles in motion. Okay, particles is we're going to be really focused on gases. Okay, so these gases are constantly moving. And how do gases move? They move in a constant random motion. But particles always will move in a gas, will always move in straight lines until they collide with another particle or wall. So for example, we will always have a particle. It will continue to go in this direction until it runs into something else and then it'll bounce off. Or if it was going, let's say, in this direction and then it collides with another particle that's going in this and then they'd bounce off. Okay, so they'll constantly go in the same motion until they run into something else. For our particle pictures, the motion of the particles will be represented by what we'll technically call whooshies. So what I want to do is I want to show you how we're going to be drawing a particle with a whooshy in this class. So a particle is drawn with a circle. Okay, you can either draw this or you can draw a colored circle if you wanted to represent different particles. And what we're going to do is we're going to draw a whooshy. A whooshy shows the speed at which it's going. It's showing movement. So if I draw a whooshy like this, that's its tail. What it's doing is it's saying that it went in this direction. Okay, the whooshy is kind of like the thing behind it, the particles behind, not the particles, but the air behind it, right? So it's telling its direction. So this one would be heading in the upward direction, that particle, okay? How do I know? Because the whooshy is always towards the end of the particle. It's where it came from. Okay, energy is a quantity that has the capacity to cause change and is conserved. Okay, what that means is that first off, you can cause change with energy, so it changes something. It can do work, whatever. But what it means that it's conserved is it's neither created nor destroyed. So the amount of energy that you start with will be the same amount of energy that you end with. It just will change its forms. Okay, energy can be transferred from the collision of particles. So when one particle runs into another particle, okay, that energy from the one particle can be collided with the other particle, right? But what we're going to assume for our particular things with particles in motion is that these collisions are perfectly elastic, meaning that no energy is lost due to friction, due to running into each other. So like if you were to bounce a ball, okay, so you just drop a bouncy ball. What ends up happening is after a little bit of time, the bouncy ball stops. And that's because not all of that energy is transferred from the ball upwards. Some of it's transferred to heat loss and things like that. Our assumption in this particles of motion for gases is that all of the collisions when a gas particle either runs into another gas particle or a gas particle runs into a wall, all of those collisions are perfectly elastic, meaning all of the motion, all of the energy going towards motion will stay in some sort of motion. Energy can change the speed of the and the arrangement of the particles. That's the other kind of thing about energy that we're going to be talking about. What does that mean? That means that if we add more energy, we can increase the speed or we can change the arrangement. So what does that mean as far as the arrangement? Arrangement is what we're talking about is the states of matter. Okay, so when we add energy to anything, okay, we are either going to be changing its speed or we are going to be changing its arrangement. So meaning for the arrangement, we had particles that were right next to each other. Let's say we added some energy. Now they are spread more apart. Okay. Otherwise, we could change its speed by making it move faster. So you have thermal energy. Thermal energy is the measurement of the speed of the particles. So if we change the speed, we change its thermal energy. In this class, we are going to abbreviate thermal energy as ETH. Okay? E stands for energy, TH stands for thermal. So if we are ever changing the speed of the particles, we are changing the thermal energy of that particles. And how do we measure thermal energy? We measure it through the temperature. So basically, if we increase its temperature, we are increasing its thermal energy. Okay, we are increasing its speed. And so when we do that, we are going to have to show that through particle pictures by changing the number of whooshies. The more whooshies means the faster it's going. Okay, so once again, as a review of this, thermal energy is the measurement of the temperature, which is really the measurement of the speed of the particles. And so if we want to change the speed of the particles, we change its temperature, either by going up or going down. If we increase its thermal energy, we are increasing its temperature, we are increasing its speed. So we're going to try to draw 3 different whooshy speeds. First off, all particles are moving in some shape or form, so everything needs at least one whooshy, okay? This would be the slowest whooshy. This would be the next. And then I'm guessing you already know how to draw something that's going faster, would be this. So if I asked you, saying that these are the same type of particles, meaning they're all water or gas, right? Which one has a higher temperature? And you should be able to tell me that this guy on the right has a higher temperature. And why does it have a higher temperature? Because it has 3 whooshies, which means that it is going faster than the guys who have 2 or 1 whooshy. So temperature is the measurement of thermal energy or the speed of the particles, as I've talked about before. So as your temperature increases, your particles move faster. Okay, so faster particles, which means you have a higher temperature, have more energy and therefore more ETH. So if I asked you which one has a higher ETH, something that is 100 degrees Celsius or something that is 250 degrees Celsius, the thing that has more ETH or thermal energy is the thing that was at 250 degrees Celsius. You can also tell me that the particles are moving faster at that stage. So let's draw a before and after particle picture of the gas being heated by a Bunsen burner. So I'm really bad at drawing, okay? But we've got this flame. Ooh, I can even make it colored. Okay, we've got this flame, right? And so we're going to draw before, and we're going to draw an after of this. So we've got the flame. We're going to heat it up a little bit, right? We're going to heat up these particles. And so first off, it's gas. So we're going to only have a few particles, okay? And so what are we going to do? We are going to have them going fast, right? Okay? But now we've heated it up. So what's going to happen? Well, these guys had better be cranking it a little bit faster. Okay? So you could either do 2, you could do 3 whooshies. I don't care as long as it somehow increases your number of whooshies. Okay, why? Because once again, whooshies represent how fast things are going. So I'm sure almost all of you guys know of the scientific measurement. What do we always measure everything in this class? Well, we measured in degrees Celsius. Surprisingly, that is actually not the unit that you measure things in the scientific community. The one that you use is probably one that you actually have never even heard of, which is Kelvin. Kelvin is the scientific metric way that we measure temperature. Okay, now what's cool or interesting is actually we still measure everything in degrees Celsius, and then we convert every single time that degrees Celsius into Kelvin. We don't ever see a Kelvin thermometer. We do see a degrees Celsius thermometer. So we always have to do this conversion, which is kind of silly. They should just do it in Kelvin right away. Now, notice first off, I didn't say degrees Celsius. It's actually just Kelvin. So instead of saying 200 degrees Celsius or 200 degrees Kelvin, you literally will say 200 Kelvin. The reason why they have the Kelvin scale is because of this guy right here. Okay, absolute zero is the pure reason of why we have the Kelvin scale. The reason why is because temperature measures movement. So if we are measuring movement, there always has to be some sort of movement. In fact, the only time that it would be zero movement would be when it was at some temperature where there could be no movement because it's so cold. And what they figured out through some basic labs is that that temperature is equivalent to negative 273 degrees Celsius. So at negative 273 degrees Celsius, all atomic structures stop movement, which means that there is no temperature. And what they did is they then converted that into a new system called Kelvin. And it is an additive system. It's very easy to convert between degrees Celsius and Kelvin. All you have to do is whatever your temperature is in degrees Celsius, you add the number 273, and that is Kelvin. So 0 degrees Celsius is equal to 273 Kelvin. Okay. Now, that is how they figured out that 0K was the coldest temperature possible. It is known as absolute zero. Okay, so absolute zero is the coldest temperature. Why? Because temperature is the measure of movement, and at 0 Kelvin, there is no movement. Therefore, it is the coldest you possibly can get. The reason why we have the Kelvin system, though, is because when we are doing some math equations, which we will get to with gases, you are going to be dividing by temperature, okay? Or multiplying by temperature, it doesn't really matter. What would end up happening is if you had let's say you knew a volume unit, okay? Let's say you knew a volume unit, and we'll say it was 3, right? And then you're trying to figure out your volume unit of something else. And we went from, let's say, 300 degrees Celsius, and we cranked it down in temperature, and we went to negative 100 degrees Celsius. If you had 3 over 300, which is what the formula would be, equals x over negative 100 degrees Celsius, what type of volume would you get? Well, you should note that it would be a negative volume, and that is not possible, okay? Not possible. So because of this desire to never get these negative values for volumes and pressures and things like that, they had to convert a new system where it would never actually get to 0. So Kelvin never can get to a negative number. The only number it can get to is 0 Kelvin, and that's only in theory. They have gotten to like a millionth of a degree out in Boulder, Colorado, but that's as close to 0 Kelvin as we get. So this is right now theoretical, but it is the lowest temperature we got. All right, so let's try some basic conversions. Remember, Kelvin equals degrees Celsius plus 273. So if we know 900 Kelvin, all you have to do is take your degrees Celsius plus 273. So we're going to have to subtract 273 from both sides. And then we will get our temperature in degrees Celsius, which is 627 degrees Celsius. Now we're going to try to convert from Celsius to Kelvin. So Kelvin, remember, equals degrees Celsius, which is this case 75.8, plus 273. So 273 plus 75.8 is equal to 348.8 degree, or not degrees, but Kelvin. Okay, hopefully you understand the basics of temperature as related to its motion, its number of whooshes, and as far as conversions between Kelvin and Celsius. Have a great one.